I will explain the essence of tensors through a few examples to introduce you to the topic. Let's take this equation here. 1 hour is equal to 60 minutes, which is equal to 3,600 seconds. You can see that we have three different numerical values which represent the exact same thing, the amount of time which is in an hour. That is the essence of the idea behind the tensor. The values you will get for it will change depending on the perspective you are adopting, in this case, the unit for time. Let's now look at this 2D vector and its xy coordinate system. We can see that if we rotate the x and y axis, our vector coordinates also change. Think of a tensor as the stuff within the vector. No matter how you rotate the axis, that vector is essentially the same thing. Now for definitions. A rank 0 tensor is a scalar, since the tensor has no direction. A rank 1 tensor is a vector. Rank 2 is a matrix, and any rank higher than this is difficult to write out, which is why we use indices, which will be explained in the next part.
Similarly to matrices and vectors, tensor components can be described using indices. These indices can easily be expressed using the covariant notation. For instance, in this example of a tensor of rank 2, which is nothing but a matrix, the index I represents the components of the row I. Similarly, the index j represents the components of the column j. By going through each row I and each column j, we can access every component of the matrix. This notation can therefore describe any tensor of any rank. It is crucial, however, to see that the name we give to these indices are arbitrary. They are dummy indices. This means that we can change their names arbitrarily as long as they don't coincide with indices of other tensors. That is why it is important that we introduce a convention, as such a notation can often become crowded and unclear. When, in a single expression, an index is repeated, this means that components of this index are being summed over. This is called the Einstein summation convention. For instance, by writing AIBI, what we're actually doing is that we're multiplying every ith component of A and B and summing them all together. In this case, AIBI is the same as the dot product between two vectors A and B, but in component notation.
I'm now going to introduce two very important tensors in tensor algebra, the Kronecker delta and the Levi-Civita tensor. The Kronecker delta has 2 indices, whereas in simple cases, the Levi-Civita tensor has 3 indices. This tells us that the Kronecker delta is a rank 2 tensor and the Levi-Civita tensor is rank 3. For the Kronecker delta, if 2 indices I and j are the same in a single expression, it equals 1, otherwise it equals 0. Dot product between two basic vectors behave exactly the same, which either equals 1 or 0. Usually, by Einstein summation convention we talked before, the Kronecker delta can vanish in an equation by replace one of its indices by the other indices. For example, delta ij ai bj equals ai bi. And for Levi-Civita tensor, if ijk is in permutation of 1, 2, 3, 2, 3, 1, or 3, 1, 2, it equals 1. If the permutation is 3, 2, 1, 1, 3, 2, or 2, 1, 3, it then equals minus 1. Otherwise, it equals 0, which means that if any 2 or 3 indices are equal for components, then it outputs 0. A way to remember this is to write 1, 2, 3 anticlockwise as the vertices of a triangle. If the permutation is anticlockwise, then the Levi-Civita tensor equals 1, and similarly, minus 1 for clockwise permutation. For example, 2, 1, 3 goes clockwise, therefore epsilon 2, 1, 3 is minus 1. On the other hand, 3, 1, 2 goes anticlockwise, so epsilon 3, 1, 2 is plus 1.
Tensors have a wide application in physics due to its versatile format for representing physical systems. These would include systems in which we have to account for multiple components acting in different directions. An example of this would be the stress and strain tensors. In this diagram, we can see a rank 2 tensor that describes the shear stress components, expressed by sigma 1, 2, 1, 3, 2, 1, 3, 1, 3, 2, and 2, 3, and tensile or compressive stress components, expressed by sigma 1, 1, 2, 2, and 3, 3. The shear stress causes the object to deform along its sides, whereas the tensile or compressive stress stretch or squeeze the object in one direction. The stress-strain tensor is an example of a symmetric tensor because the value of sigma 1, 2 is equal to sigma 2, 1, and similarly, sigma 1, 3 is equal to sigma 3, 1, and so on. Tensors are used in various branches of physics like quantum mechanics, and it essentially underlies general relativity.